Hello and welcome to all students. In this lecture we learn about congruence relation on Z. Okay, and we discuss about the points. The outline of our lecture is first of all we see some introductory part, introduction. Secondly, we see the definition of congruence relation modulo n. Then we see some remarks. After that we see some examples on congruence relation, and then we see the alternate form of a definition of congruence relation, not GCD, congruence relation, and then finally we see the theorems on congruence relation. Okay, so in introduction we discussed integers and their divisibilities in the previous chapter. So we know that the what are the integers and what is a divisibility in Z. The divisibility property leads to one of the most important property on Z, and that property is known as congruence relation on Z. So we define what is mean by the congruence relation modulo n, or we define what is the congruence relation on Z. So let n be a positive integer. An integer a is said to be congruent to integer b modulo n if and only if a minus b is divisible by n. See the definition. Definition is very simple. So it is the definition of a is congruent to b modulo n. So when we say integer a is congruent to an integer b modulo n, if and only if the difference a minus b is divisible by n. That is the very simple definition. म्हणजे a मायनस बी हा जो डिफरन्स आहे तो n नी डिव्हिजिबल पाहिजे. म्हणजे n नी a मायनस बीला जर भाग दिला तर पूर्ण भाग गेला पाहिजे. म्हणजे बाकी जे आहे रिमाइंडर मस्ट बी 0. ओके, रिमाइंडर मस्ट बी 0. So when we divide by n to the difference a minus b, then we must get a remainder 0, or we can say that a minus b is divisible by n, or we can say that a minus b is in multiple of n. Okay, so all these things are one and the same. So this is the very simple definition of congruence modulo n. And we denote it by we denote this thing by using the notation a is congruent to b modulo n. So this is the sign of equivalent sign. हे जे तीन रेषा दिसतात ती साइन कशाचं आहे, इक्विव्हॅलंटचं साइन आहे ॲक्च्युली, परंतु त्याला आपण कॉन्ग्रुएंट असं रीड करणार आहोत. ए इज कॉन्ग्रुएंट टू बी मॉड एन अशा पद्धतीने. ओके, सो and it is denoted by a is congruent to b mod n. Thus given a positive integer n, a is congruent to b modulo n if and only if n divides a minus b. N divides a minus b. That is very important. Okay, this is the short of this above definition. Thus given a positive integer n, we say that a is congruent to b mod n if and only if n divides the difference a minus b. Very simple and very easy to understand. We write some remarks based on this definition. So here A is congruent to 0 mod n if and only if n divides A minus 0, and this is if and only if n divides A. So if n divides A, then we can say that A is congruent to 0 mod n. Or if n divides A, then we can say that A is congruent to 0 mod n. Very simple. So here for example 5 divides 10. 5 divides 10. So we can say that 10 is congruent to 0 mod 5. Simple. Okay. One more example. 3 divides 9. Therefore, we can say that 9 is congruent to 0 mod 3. Very simple examples. Okay. So, and now the second remark is when n is equal to 1, when n is equal to 1, A is congruent to B mod 1 if and only if 1 divides A minus B, and which is always true for all integers A and B. Therefore, for any two integers A and B, we can say that A is congruent to B mod 1. See here. Once again, for any two integers A and B, we can say that A is congruent to B mod 1. It is always true. Okay. Therefore, A is congruent to B mod 1 for all integers A and B. This is our second remark. Now, remark number 3. When n equal to 0, then A is congruent to B mod 0. This means if and only if 0 divides A minus B, if and only if A minus B is 0, so 0 divides A minus B means 0 divides only 0. So A minus B must be 0. If and only if A is equal to B. So finally, if A and B are same, then we can say that A is congruent to B mod 0. Means 5 is congruent to 5 mod 0. That is true. 10 is congruent to 10 mod 0. That is true. Okay. So if A and B are same, then this is true. A is congruent to A is congruent to B mod 0. For example, we can write 5 is congruent to 5 mod 0. Okay. So like this. Thus A is congruent to B mod 0 if and only if A is equal to B. Now fourth remark is, by division algorithm, if we divide A by n, then there are integers q and r such that by division algorithm, if we divide A by n, then there are integers q and r such that A is equal to nq plus r, where r is greater or equal to 0 less than n. So q is a quotient and r is a remainder. A minus r is equal to nq. Okay, from above equation we can write A minus r is equal to n into q. Therefore, so see here, A minus r is in multiple of n, Therefore, we can write A minus r, or we can say that n divides A minus r, or we can write A is congruent to r modulo n, or we can write A is congruent to r modulo n. So see here, Once again, if we divide a by n and if we have a remainder r, then we can say that a is congruent to r modulo n, or we can say that a is congruent to remainder modulo n. So r is the remainder. Here we write always the remainder. So whenever we divide a by n, then we write here r as a remainder. Okay, so a is always congruent to remainder modulo n. So when a is divided by n, then a is always congruent to remainder modulo n. That is also very important, keep in mind. Okay, now some examples on congruence. See the first example, 3 is congruent to 7 modulo 4 because 4 divides the difference of 3 and 7. See here, since 4 divides the difference 3 and 7, difference of 3 and 7. So difference of 3 and 7 means 3 minus 7 is minus 4 and 4 divides minus 4. Therefore, we can say that 4 divides 3 minus 7 and therefore 3 is congruent to 7 minus 4. So this is also very easy. Now consider the second example, 5 is congruent to minus 43 mod 16 because the reason is 16 divides 5 minus minus 43 and 43 means 48, sorry, 5 plus 43 is nothing but 48 and 48 is in multiple of 16. 16 into 3 is 48. That's why 16 divides 48, or we can say that 16 divides 5 minus minus 43. Therefore, we can write 5 is congruent to 43 modulo 16. Okay, so this is also easy. Now next congruence relation is 93 is congruent to 51 modulo 7, or modulo, here it is short notation is mod. 93 is congruent to 51 mod 7 because 7 divides 93 minus 51. 93 minus 51 is 42 and 7 divides 4 to 42. Okay, so as 7 divides the difference 93 minus 51, therefore we can write 93 is congruent to 51 modulo 7. Okay, now there is an alternate form of definition of congruence relation. Okay, so we know that A is congruent to B mod n, and it is true if and only if n divides A minus B. That is the definition, given definition. So we know that A is congruent to B mod n if and only if n divides A minus B, and n divides A minus B if and only if there exists integer lambda such that n is equal to lambda times A minus B. So n divides A minus B. This means that A minus B is, or we can say that n is in multiple of A minus B. Therefore, there exists an integer lambda such that n is equal to lambda times A minus B. Thus, finally, we can say that A is congruent to B mod n if and only if n can be expressed like this: n is equal to lambda times A minus B for suitable integer lambda. So this is one more definition this is the second definition for congruence relation. A is congruent to B mod n if and only if n is equal to some integer lambda times a minus b. Okay, so this is also important, we keep in mind this definition. So let us see theorem on the congruence relation modulo n. The relation of congruent modulo n for any fixed positive integer n satisfy the following properties. The relation of congruent modulo n for any fixed positive integer n satisfy the following properties. So first property is a is congruent to a mod n for all a belongs to z. So this property says that if a is any integer, then integer a itself, that integer a is congruent to itself modulo n. Okay, so any integer a is congruent to itself modulo n for all a belongs to z. So this property is called as a reflexivity. Means integer is congruent to itself. Okay, modulo n is any integer. So this property is called as a reflexivity. Now second property is if a is congruent to b mod n, then if a is congruent to b mod n for any two integers a and b, then b is also congruent to a mod n. Okay, and this is also important. If a is congruent to b mod n, then b is also congruent to a mod n. And this property is called as symmetry. Now third is if a is congruent to b mod n and b is congruent to c mod n for any three integers a, b, c, then a is congruent to c mod n. And this property is called as transitivity. Okay, so let us try to prove this theorem now. So we prove this theorem in three parts. In first part we will prove that a reflexivity. In second part we will prove that symmetry, and in third part we prove that the transitivity. So write the proof. Let n be a positive integer in Z. Let n be a positive integer. It is not necessary to write in Z. It is a positive integer. Okay. We know that for any AB belongs to Z, A is congruent to B mod n if and only if n divides the difference A minus B. Very simple. This is from the definition, or this is from the alternate definition of congruence relation modulo n. So once again, A is congruent to B mod n if and only if n divides A minus B. The required properties are established as below. First we see the reflexivity. Since n divides 0, any integer n divides 0, that is n will divides a minus a, and this is true for all a belongs to Z, and therefore A will be congruent to A mod n for all A belongs to Z. So this is the proof of reflexivity property, and that proof is very simple. Okay. Now we prove the next property of the congruence relation. We call it is symmetry. For this, let us take A and B be any two integers such that A is congruent to B mod n. Therefore, by definition of congruence, n must divide the difference A minus B, which is turn implies that n divides the negative of A minus B, and this implies that n divides minus A plus B, and this implies that n divides B minus A. Therefore, from the definition of congruence, B must be congruent to A mod n. Thus, here we have proved that whenever A is congruent to B mod n, this implies that B is also congruent to A mod n. Thus, the symmetry property we have proved. Now, let us prove the third property. We call it is transitivity. Let A, B and C be three integers such that A is congruent to B mod n and B is congruent to C mod n. Therefore, by definition of congruence, n divides A minus B and n divides B minus C. Therefore, by definition of congruence, we can write n divides A minus B and n divides B minus C. If we add as n divides A minus B and n divides B minus C, then n must divide the addition of A minus B and B minus C. Therefore, n divides A minus B plus B minus C. So this implies n divides A minus C, and it gives, by definition of congruence, A is congruent to C. A is congruent to C mod n. Thus, here we have proved that whenever A is congruent to B mod n and B is congruent to C mod n, then it gives A also congruent to C mod n. This property is known as transitivity of congruence relation. Okay, thus all these three properties are proved. So as the congruence relation satisfies all these three properties, therefore the congruence relation is also known as equivalence relation. Congruence relation is also known as equivalence relation. Okay, so in this lecture, if you have any problem, you can contact me. Okay, let us stop our lecture here. Thank you very much.